colloquium. I'm Jeff Boker, co-chair for the series, and it's my great honor and pleasure to introduce today's speaker, Professor Sayeef Salahuddin, who is the TSMC Distinguished Professor here in Berkeley. And Professor Salahuddin is very well known for a variety of breakthroughs, most notably his invention or discovery, depending on how you want to put it, of something called negative capacitance, which I don't know if he's going to hint at today, a little bit maybe. But he will talk more broadly about what some of the new trends are that, believe it or not, CMOS is going to continue to improve and evolve and provide ever more powerful information technology for us all. I just want to note two things. Honors that Professor Salahuddin has won. One is the Presidential Early Career Award for Scientists and Engineers, the PECASE. It's a very prestigious award. And even more so is the IEEE Andrew Grove Award, which is for outstanding contributions in solid-state devices and technology. And Professor Salahuddin is giving us a talk right now on new pathways for energy-efficient hardware. And we're going to hear how Moore's Law is not dead, I hope. Good one.
All right. All right, thank you, Jeff. So, you know, at my job, I have to give presentations all the time, but I can say that this morning when I was thinking that I'll actually present here at Berkeley, it made me nervous. So, it's my honor to be here and talk about some of our research and how we are thinking about the future in terms of energy efficient hardware for computers. Our work is mostly on the technology side and the component technology, so that's what I will mostly talk about. But I'll start with this this slide that these days I start almost every one of my presentations with is this fact that information processing, when we think about computers, often, at least those of you who are of my generation, we think about a computer with a screen, a keyboard, and all of those things. But often what is lost is how it has become a part of our daily life, right? So if you think about information processing, we are not only just crunching numbers, but our economics, our food distribution, trying to find the remedy of a pandemic in record times. All of those things today depend on computers. So, and this involvement of computers in our daily life is increasing all the time. So these days, I often, because of the Chips and Sciences Act, I often have presented at various venues. But this is a point I want to make, that when we talk about a future which is sustainable, where we are actually making the best use of our resources, that plan is intimately integrated with how well we will use our computers, because all those optimizations come from very large scale computing. From economic point of view, if you actually follow the trend, the semiconductor industry, the computing side as a whole is approaching $1 trillion trillion of market, which is like a single percentage of worldwide GDP. So again, if you think about it, it's a very large number, and it keeps going up. So that shows how important it is for our modern life. Now, today, of course, when we think about computing workload, it's all about AI. AI has taken us by storm, right? And so this is the NVIDIA Blackwell chip that recently came out. And the point that I wanted to make is that it has 208 billion transistors. Okay, says 208 billion transistors of TSMC 4NP, which is basically a plus version of their N5, the 5 nanometer node. But if you just pause and think about 208 billion transistors, something that is made of that many components, and they are all working together to give us something functional, it's kind of amazing. But it also says that we need to make our transistors smaller and smaller because you have to pack 208 billion transistors on a manageable area.
What is the dimension?
Dimension of the chip? I don't know. That I can find out for you. Yeah. But you.
There's two reticle limited dies. So
Right. So,
those are like 20 millimeters on the side each.
right. It's often not fully square even also. So we can. I can take a look. Yeah. So the other thing is you have to power these 208 billion transistors. Again, if you think about the AI workload, we are doing a lot of linear algebra. So you are doing matrix vector multiplications. And as a result, you are taking these very large, very wide words, and you are multiplying them together at the same time because you're going component-wise multiplication. So you are turning on massive amount of transistors in parallel. That's a very different use of transistors than what we are used to. So essentially, you are turning on many, many transistors together. Now, from the universities, people had already said in the previous years that this is a problem because that means that you are spending a lot of power by trying to run all these transistors in parallel. We only recently are starting to hear it from the industry, the people who are actually designing the AI chips, and they are starting to say it publicly that it is often not possible for them while doing these calculations to run the transistors at their VDD, the supply voltage that is spec'd. So they are actually running them at a smaller voltage to be able to do these calculations within the power budget of the server. We are also seeing news articles coming out, which sounds kind of surreal, but the data centers are starting to plan that they will be powered by nuclear power reactors, right? Because that is the amount of power that is necessary. So one of the things that is also part of this story, it is not only about transistors, all.
Problem to getting the power in or the heat out?
Both. Getting power in is a generation problem. Getting heat out is a significant problem in the chip design today. Yeah. So there is another part of this story, which is the use of memory. Traditionally, we have built our computers where processors and memory were separate, and what that means, and all AI workloads require significant amount of memory. So typically, the way we do this today is that we have this stacked DRAMs that we put through an interposer with our GPUs and CPUs, and you are trying to access them through the interposer. Because of that communication, typically we need 50 picojoule per bit and 30 nanosecond access time because you are essentially going outside the chip to communicate to your memory. And so this is also limited by the bandwidth, meaning how many bits can you access in parallel. That also is a function of how much power you have to spend per bit and the access time itself. Okay. So if we think about what are the challenges that we are looking at, the first one is running devices at a smaller and smaller energy, because if we are going to need more and more devices on our chip to address larger and larger workloads, we have to reduce the amount of energy we spend per device. Again, remember that 200 billion transistors already today. The next one will have even more. So we have to do a very good job of reducing the energy per device. Going to smaller and smaller devices is always necessary because If you try to process larger and larger chips, then yield goes down. I remember a veteran from IBM once told me that apparently there is a saying in the industry which says big chips sink ships. So, so you do not want to go to larger and larger chip area. In fact, because of that, dilate integration, integrating many chips together, is becoming a big push in the industry, because you can work with smaller chips with high yields and then try to integrate them. But that comes with its own challenges and all, but there is a real need for that. And of course, access to more and more memory faster and at smaller energy. So these are some of the challenges for us. And I kind of, again, feel like that, again, if we are thinking about a sustainable future where we need a lot of computing, these are some of the pressing challenges of our time that we need to address. Okay. So next up, what I'll do, I'll spend like 5 minutes on some stuff that many of you actually already know probably better than me. But these are some slides from our EE 130 class, where I talk about just transistor as a switch. So transistors are essentially nothing but a switch. You have two terminals and you want to control current going through going from 1 to 2 or 2 to 1 by changing this control switch. So the idea is that you apply a voltage here, you let the current flow, you turn it off, then current should not flow. And the way we implement this idea is what we call this transistor, where we have a silicon and we have these doped regions from where electrons can come, and our control is done through an insulator across which we apply a voltage. So there is a field that comes in and then tries to control the current flow through the transistor. So this is why we often call this a field effect transistor. So this is an insulator. So this insulator has a capacitance. Silicon is a semiconductor, which is essentially an insulator with a low band gap. So it also has a capacitance. So if we look at this structure, it is basically a series combination of two capacitors. And if I want to look at this voltage here, I use the capacitance divider formula, which gives me Cox divided by Cox plus C silicon times dVg. So that's the voltage at this middle terminal, which is right at this surface. The reason we should look at it is that if we now also look from source to drain, because of this doping differences, these two are heavily doped inside, not heavily doped. So there is an energy barrier that looks like this coming from source to drain. Here, I have also assumed that I have an applied voltage in the drain end. And so what happens is, when we change this potential here by applying a voltage here, this barrier comes down. So when we increase Vg, this barrier comes down, and electrons are fermions, so they follow the Fermi distribution at the source. So as the barrier comes down, I increase the number of electrons that can go from left to right, because these orange electrons can now go from left to right. And because of the Fermi distribution, the number that becomes available that can go from left to right increases exponentially. So this is why when we apply a gate voltage in our transistor, current goes up exponentially. That's what we see here. This is a current versus gate voltage plotted in a semi-log scale. So this is a log scale. Here we see a linear dependence because of that exponential increase in the electrons. So this allows us to essentially turn on and off the device with a gate voltage, and that's how we use our transistors. But what happens is, when we make the device much smaller, the drain end now comes very close to the source end. So this drain end now introduces another capacitance, because I have another essentially metal contact here. And when we take care of this capacitance by solving this 3 capacitor network, this CD appears at the bottom. So CD appearing at the bottom essentially means that by applying the same amount of gate voltage, I can no longer change the Sayeef by the same amount. In other words, I have lost my gate control, which in a real device shows up like this. So this is from a long channel device. This is from a shorter channel device. And you can see that for the same amount of gate voltage, the off current is much larger. And we cannot turn off the device anymore. So this is the problem, that as we try to reduce the channel length of the transistors, we start losing gate control. So if you look at this very simple equation, you'll see that I have C silicon, I have this drain, which is capacitance, which is coming because drain is coming close to the source. So the only way that I can get back the gate control again is making Cox very high. If Cox is very high, if Cox is so large that these guys can be completely ignored, then this IS becomes DVG, which means I get all the voltage that I apply at the gate to come here. So if you look at our scaling history, how the industry has tried to reduce their device dimensions, to the first order, they have actually followed it. Okay, so if we look at that, we will come back to that question in a minute. But as I said, that increasing Cox helps us to get back the gate control. But when we also look at the current that we will get, the current is charge times velocity. This is just very fundamental. You have some charge and you look at the velocity that gives us that product gives us the current. So charge becomes C times a voltage. So this is the gate voltage, and VTH is what we call a threshold voltage. Essentially what we need is a small amount of voltage that gives us a range for the transistor to be off. So after this threshold voltage, when I apply the additional voltage that I apply gives me this inversion charge that we call the inversion charge, and that times velocity gives me the current. So from here, what you can see that if Cox goes up, it also helps us to get the same current at a lower VG, which then allows us to reduce VD as well. So if we again look at the scaling trend, over the years, what has happened is that for as we came down in channel length, our VDD has also come down, but it is starting to saturate out. And we will discuss more about that. Now, as I said that overall, the industry has followed this scaling path. If you look at this as an insulator, the capacitance is given by the permittivity. If I think about this as a SiO2 divided by the effective oxide thickness. Why we call this effective, I will talk about it a little bit, but this is to some extent a normalized thickness of this oxide. So the first thing that happened is that we went to a higher permittivity oxide. So that is what is called the high K-metal gate transition. This happened in Intel's 45 nanometer first, and I see Dr. Tahir Ghani here, who actually led that effort from Intel. So that is how we first moved in the scaling path. Then came FinFET, where the early work, the original work was done at Berkeley by Chen-Ming Hu, Professor Boker, and also Professor Sujie King Liu. So here the idea is that you are wrapping your channel with the gate from two sides, which is kind of increasing the Cox by 2 times. Okay, so even for the same kind of a oxide, just because I have now 2 gates, the Cox to the first order goes up by 2 times compared to the other capacitors. And now we are moving towards what we call the gate all around transistors. So basically this is the channel and this whole thing is wrapping around it. So you are trying to wrap around the channel from 4 sides and thereby trying to increase the capacitance even more. So again, just as a summary for that scaling pathway, this was our transistor. We first changed the dielectric to have a higher permittivity to give high COX. Then with that high COX, we went to double gate, and now we have 4 gates. Okay, so that's how we are pushing the transistors more and more and more. Okay. So now with that context, we are at the university. So what we want to do is we want to look at, what can we do that is not in the regular roadmap. It's not in a regular way of scaling pathway, right? So we said that we should look at this material, this set of materials like ferroelectrics for increasing COX. And I'll try to explain why we wanted to do that. But first up, the difference between a standard dielectric and a ferroelectric is shown here. For a standard dielectric, the energy landscape looks like a parabola. For a ferroelectric, it looks like a W. And this W gives us all kinds of interesting effects. So let me go there. So ferroelectric material are typically a dielectric and typically an insulator material. And what it has is that it's in its unit cells, there are dipoles. What that means is that there is a metal atom which is slightly shifted from the center of the unit cell. So if the metal atom is slightly shifted, it creates an electric field. And so now you can imagine that you have all these unit cells all over your material, each one with an electric field. So they start to interact with each other. And this interaction then stores some energy, because all these electric fields will start to store some energy in the material. That stored energy provides us with this middle part. So it would have been a parabola, like a standard dielectric, but this stored energy gives us this middle part, thereby giving us a W-looking energy landscape. So if we now look at there, if we look at here, we can see that this is an inverted parabola, this middle region. So if I'm trying to fit a parabola here, I have to assume that capacitance is negative because Q square is positive. So this allows us to have an interesting regime of operation for this material, where unlike conventional materials, the capacitance is negative. But what we can also see that this region is not the minimum energy position for the material, so the material will not be stable there. So we have to find a trick to push it there, and I will say why we want to use this material in a minute. But think about this W energy landscape, and let's say that I put a parabola with it. If these two are added properly, then we will get this green parabola, okay? And y-axis is U, x-axis is Q, so you can see that to switch the same amount of Q for the green, I need a smaller energy than the orange. So that means that I'm switching the same amount of charge at a smaller energy, which means that capacitance must have gone up. So I'm putting two capacitors in series. Our standard textbook will say capacitance should always go down. But in this case, capacitance can go up, and that gives us something that is not traditionally possible. And you can now see the relationship to the transistor is that if we can do this, we can unconventionally increase COX and therefore help with both VDD scaling and scaling down the dimensions of the transistors. Okay, so we showed this effect first in an experiment back in 2011 from here. So this is many years ago now. But we were able to show that you have a dielectric and you put a ferroelectric on top. So you have increased the thickness. Convention will say that capacitance should go down, but here the capacitance went up even by 2x. And later on, many experiments, we were able to show that you can get 4x, 5x increase in capacitance. Again, very unconventional. And one of the things, although we have mostly focused on looking at transistors, at that time, this is an excerpt from the conclusion of the paper that the enhancement in capacitance in this way can help other applications like DRAM and like supercapacitors. Okay. Okay, so much more recently what we have done is we have worked on materials that we can actually integrate with silicon transistors, advanced silicon transistors. So here I'm showing a structure where I have hafnium oxide, zirconium oxide in a tricolor fashion. And so zirconium oxide has a permittivity of 40, hafnium oxide has a highest permittivity that we can get is around 29, and zirconium oxide, again, another 40. Typically, when we put these materials together, again, classically, you put capacitors in series, capacitance goes down. But here, what we have been able to show that you can get a permittivity which is larger than all of these constituent permittivities. So again, this is this non-classical increase in the permittivity of the system. So this allows us to then start using these things for transistor applications. So just one thing before we go into actual transistor results, is one of the things that we discovered while doing many experiments on various kinds of systems is that when you think about these ferroelectrics, they have permanent dipoles, so they have these, there's polarization vectors. What we found is it is in between these highly polarized regions, where in this community we call that a domain wall, where polarization is heavily suppressed is where we get the negative capacitance. We have been actually able to image that using the capabilities we have up at the Hill at Lawrence Berkeley National Lab. So that's what, this is something that follows our theory as well. You see that negative capacitance happens when polarization or charge is very close to zero in this ferroelectric material. So in this regime, when it is going from highly up to highly down, in the middle region, it has to go through zero. And this is like a frustrated state for polarization where the negative capacitance shows up. Question?
Can you actually get a negative? Because I would think that would always be thermodynamically unstable. So I could see how you could maybe make the sum of them suddenly zero when you expect it larger. But if you had to actually, so maybe conceptually you add a negative capacity to make the whole thing bigger, but you can't really have a negative capacity.
You are absolutely correct. When we are looking from the entire system, it cannot be in negative capacitance region. It will be thermodynamically unstable. Therefore, it will give us what we call a hysteresis. It will switch between two states. However, what we can do, and this is what we have imaged, that we can locally stabilize this negative capacitance region, which is surrounded by positive capacitance regions. So when you measure from outside, you still see a positive capacitance, but it is highly enhanced than what would otherwise be. Yeah. All right. So now with that understanding, we can look at some of the gate stacks that we have made, the gate oxides here at Berkeley. So this is a silicon substrate. And then what we have is SiO2. We need this SiO2 in silicon transistors to make sure that electron transport property in the silicon is not affected. And typically there is a way to do this. This is called a chemical growth, which is self-limited. So it actually gives around 8 angstrom silicon dioxide for everybody. Even in our advanced transistors, that the same process is used, and it is around 8 angstrom. And then we have our magic material, the negative capacitance material. It has the same thickness that is nominally used in our advanced transistors. It's around 18 angstrom. Okay, so if we look at the EOT, remember that COX is permittivity of silicon dioxide divided by its thickness. But here it's a composite material. I have silicon dioxide and then I have something else. So what happens is we have to add the thickness of silicon dioxide and then add the thickness of this dielectric layer normalized by the permittivity ratio. So that's why it is often called the EOT. So if you look at it, what we expect to get is 8 angstrom from silicon dioxide plus something. And so here I'm showing a data from a publication for an Intel NMOS transistor where EOT is around 9.5 angstrom. Okay? But for the same kind of structure with the similar thickness, what we get here is 6.5 angstrom. So if you look at it, you really cannot get it just using this unless you think that EOT of this gate stack is adding a negative contribution. Okay, so what does this extra capacitance give us? So here are some results on 30 nanometer channel length transistors that we built here at Berkeley. So this is I-on-I-off directly measured for a VDD of 1 volt compared to some published data for similar channel length transistors from TSMC. So you can see that our on current is larger, off current is smaller. And this is with the fact that our source drain resistance is much worse than what TSMC can do. This is a university made transistor, and still there is no projection here. This is directly head-to-head measurement. And we can get higher on current and lower off current. And we are getting this simply because our charge is much higher. Our capacitance higher, and so the charge is much higher. And if you look at this quantity that we often call the transconductance, it's essentially capacitance times average velocity. You can see that effect as well as we reduce the channel length. This is 22FDX, which is a global foundry technology commercially available. This is how its trend looks like. This is how our trend looks like. So at a much longer channel length, we can actually get the same kind of transconductance that is obtained in a commercially made technology. So this is where this EOT scaling gives us an advantage. And basically what it shows is that I could have reduced my voltage to match the same on current. And that is where the VDD scaling comes from. My capacitance is also higher, so in principle, my short channel effect will be better, which shows up in the off current of the transistor. Okay, so where are we going with this? What is the roadmap here? The roadmap is that right now I showed you a result with 6.5 angstrom EOT. Now at the group, we can go down to around 4.5 angstrom EOT. So over the years, we are slowly coming down, and we will continue to go down. That's the roadmap. And at some point, we even want to go down below 0. Okay? In other words, we will have this layer contribute more than -8 angstrom to the entire stack, so that silicon can directly see the negative EOT effect. So that's how where we are going. And so if you now look at this VDD scaling curve, you can see that if just in a first order effect, if I can increase this C by 2x, in principle, I can reduce this VGS minus VTH by 2x. So we should be able to significantly reduce the VDD by going this way. And so one of the targets that we have set for ourselves is that can the VDD be scaled down to 300 millivolt or even below, right? So that's something that we want to do. Again, I'll come back to that in 3-4 minutes. But I want to, at this point, remind ourselves that we are talking a lot about transistors, but this effect that we have been working on, it gives us an unconventional increase in capacitance. So the increase in capacitance itself has all kinds of use. And so since 2020, we have seen that use show up in our actual product. So this is a Intel, actually this happened starting from 2020, so that's 10 nanometer. So in what we have seen is that in Intel 10 nanometer, the backend capacitors now actually use hafnium zirconium oxide layers, 3 layers of hafnium zirconium oxide and 1 layer of hafnium aluminum oxide. So hafnium aluminum oxide is there because aluminum oxide has a much larger band gap. It reduces the leakage current. And hafnium zirconium oxide gives you the capacitance. So you can again see that zirconium has a permittivity of 40, hafnium oxide has a permittivity of 29. If you are trying to increase capacitance, you will never add hafnium oxide with zirconium oxide because you can only get smaller. Except that if you are in that negative capacitance regime where the ferroelectric boost gives you a higher capacitance. And so this is now already used starting from Intel 10 nanometer node. We have also seen this use in Samsung's 1Z DRAM. Again, it went into production in 2020. DRAM is very well known that it uses a material called ZAZ, which is zirconium oxide, aluminum oxide, zirconium oxide. But from 2020, what we have seen is that this hafnium dioxide layer was introduced. Again, this is to help with increase in capacitance, which then allows them to reduce the area of the DRAM cells. So in our group recently, we have also looked at just looking at making very high density capacitors. So here are some results. I'm not going to get into the details a lot, but what I wanted to say, yes, I mean, you can make these capacitors, a very high density capacitor, and therefore can store a lot of energy there. So you can see that we can kind of match the commercially available micro supercapacitors, but these are made based on polymers. But our capacitors are solid-state capacitors, so we can charge and discharge them very fast. So the power density is like 5 orders of magnitude larger. Okay, so we are, already there is a lot of need for high-density capacitors at the back end of the chip for power delivery. We are actually working with Professor Robert Pilawa's group here to look into some of those options. However, there are interesting applications that you can think of. Can you actually use these capacitors to store energy? For example, to support the standby power of your SRAM for a few hours. That way, your SRAM kind of becomes non-volatile. Can you provide the boost that you need to turn on your display, like your cell phone display, when we go from a standby mode to turn on the screen, I suddenly need a lot of power. That could have come from a capacitor sitting there and used as an energy. So we are looking into some of those options. I wanted to now, these are very practical applications. I wanted to come back to the conceptual side of the negative capacitance a little bit. As we said that this negative capacitance comes from the fact that the material stores some energy because of these dipoles interacting with each other through these electric fields. So this interaction actually gives us something very interesting, and that is that if we are switching the state of the ferroelectric material, going from one state to the other, then we can look at the thermodynamics and ask that what will be the total dissipation in energy. So total energy is always conserved, so for an isothermal process, total dissipation is equal to the total change in the free energy, and the entropy is proportional to log of W, where W is the degree of freedom. So now if you think about electrons that are completely non-interacting, if you have n electrons that can switch between two states 1 and 0, their degrees of freedom is 2 raised to n. But if they're all interacting strongly, then their degree of freedom is just 2. Okay, so I often explain this using this picture of 7 kids. If they could stand up and sit down any way they want, there are 2 raised to 7 ways of arranging them, right? But if you make a rule that they have to hold their hands together, now in the limit, there are only 2 states. They can all stand up together or sit down together. So the degree of freedom comes down from 2 raised to n to just 2, which essentially means that we can reduce the dissipation in switching the state in this system from nkt to kt at the limit. Okay, so that's very interesting because how it translates to our transistors is that this means that this curve, as I'm turning on the transistor, can be as sharp as you like, as steep as you like, as long as the total switching energy is larger than kT. We are very far from that still. But with proper materials engineering, as we keep optimizing our negative capacitance effect and others, we should be at one day able to go there. So The point that I'm trying to make is that negative capacitance can lower VDD, but it is well beyond just EOT scaling. It's well beyond just CMOS scaling. If we can make that curve very, very steep, then we can also reduce the VTH, our off voltage. That will further reduce our VDD. And so that's why I said that can we push down the VDD to 300 millivolt or even lower. Okay. Now, ferroelectrics, of course, has this double degeneracy separated by an energy. We tricked it for negative capacitance to work here, but we can also work in this switching regime where we are going from here to there or there to here, in which case we will have a memory, and there is a lot of work that is going on in various kinds of memories using ferroelectrics. Some of the, our group at Berkeley is also working on various ideas. The idea there is that because this material is, one can integrate it with silicon, you can now have a lot of memory on the chip itself. So rather than going off chip, you should be able to use this on chip memory. In the interest of time, I'm not going to get into the details of this. But I want to come back to this scaling picture again. VDD scaling and transistor scaling. So we have talked a lot about CMOS. We have talked about now VTH as well. What about the transport, the velocity? Can we do something there? So it turns out, it's actually something that I did, the calculations I did during my graduate school as a homework problem. So it's not something, what I'm going to talk about now is not something that is very new. And that is that it was known for a long time that if you thin down silicon, which is otherwise an indirect bandgap material, becomes a direct bandgap material. In fact, in the late 90s, many people were very excited that this will make silicon optoelectronic, which did not happen because although it becomes a direct bandgap material, the sp orbitals don't really couple, so it's not an efficient optoelectronic material. But the fact that this indirect bandgap goes up and the material becomes kind of direct, that happens. And the thing is that as it starts to go up, your effective bandgap is going up. But at the same time, now this higher energy electrons starts to contribute to the transport. And these higher energy electrons has lower effective mass. So in principle, if you thin down the silicon, the velocity may actually go up. Okay? So without knowing or understanding the implications of this, as I said, that as a grad student, I did these calculations, mostly to show that this becomes a direct bandgap material. But in those calculations, what was already known that the overall velocity actually goes up. So we wanted to go back there. And what we did is, a few years ago, we measured a 22 FDX technology from Global Foundries where directly measuring the transconductance over capacitance, remember the transconductance is capacitance times velocity, we could get a velocity that is very close to 1e7. Now, this 22 FDX has around 5 nanometer thickness, it's quite thin. And if you believed that silicon, nothing changed in silicon band structure, you would say that this device is working at 90% of the highest velocity, the ballistic velocity of a bulk silicon transistor, which makes no sense. Because there are many other measurements you can do to show that this device is actually 50% of the highest velocity that you can achieve. Okay, so this showed us indirectly that definitely there seems to be a velocity increase as you thin it down, but we wanted to go much thinner, and Al may smile about it, but took us more than 2 years to build the thinner transistors that we wanted to build. But when we did it, this is a transistor that has, that has 3 nanometer silicon sitting on an SiO2, and then this 8 angstrom of IL, and then our negative capacitance gate stack. And if you look at our current voltage characteristic compared to the 6 nanometer, at 3 nanometer, current actually goes up. Okay, and this now shows that even in a 3 nanometer silicon, where we actually see very strong quantum confinement effects, the velocity is going up. So this allows us to work on the transport part of our scaling curve. So going down to thin silicon has other advantages. If you go down to thin silicon, you can also scale down the device. You can reduce the channel length of the device. It takes a little bit of work with Poisson's equation to see this, but there is an intuitive way of looking at it. If you have a silicon sheet and you have gate from two sides, the longest distance from the gate is the middle part of your sheet, right? So if you reduce the thickness of the sheet, that the longest distance becomes shorter, so gate gets more control. So when people did these calculations long time ago, solving Poisson's equation, they said that in principle you could have reduced your gate length to thickness over 2, which means for our demonstration 3 nanometer, this will say you can get down to an LG of 1.5 nanometers. I will say that this is a little bit too aggressive, but we say that at 3 nanometers thickness, you should be able to get down to around 6-7 nanometer of LG. But if you can reduce it down to 2 or even 1, you could go down below 5 nanometer LG. Okay, so this is my last slide. So basically what I'm going to say is that if you now look at, let's say, gate all around transistor with a negative capacitance gate, negative capacitance allows us to increase COX. That helps us to reduce the channel length and reduce voltage. If we can do really well, it will also let us reduce VTH. That allows us to reduce voltage. If you go to this very thin silicon, it increases velocity, it allows us to reduce voltage. If you go to very thin silicon, it allows you to reduce the channel length, and that has a positive, reducing channel length has a positive feedback effect, because if you reduce it smaller and smaller and smaller, electron has to go a shorter distance to go from source to drain. That means its velocity can start to approach its ballistic velocity. That way its velocity goes up even more, which then reduces the voltage even more. So starting from very fundamental physics considerations like thermodynamics in an interacting system, or quantum confinement in very thin silicon, we now see ways that are very non-traditional but can have a significant effect on transistor performance in terms of its dimension and in terms of how small a voltage it can run on. So we are these are our moonshot targets now. Can we get down below 5 nanometer LG? Can we get down to around 250 millivolt? So we are very excited about the days ahead where we would look into if we can actually get there. Okay, so with that, let me just say that everything that I present is due to my students and postdocs. They do all the work, so all the credit belongs to them. And of course, our sponsors, without whom none of this would happen. So with thanks to them, let me stop. Thank you.
Okay, questions? Let's go to a student first. I guess that. Well, you're closer than Alp anyway to being a student. You'll be next.
So you showed at the end this 3 nanometer silicon body thickness. I was wondering why for a higher gate overdrive, the ion percentage increase seems to grow.
Here?
Yeah. Or maybe it's just...
Yeah, I think it's what happens is this part is sharper, which you would expect. That's why initially it is like that, but it's saturating out, as you can see. I mean, to fully answer your question, we need to extract out the RSDs from here. We have not done that. This is directly measured data.
What do you think the fundamental physical limit of the gate length is?
So this is an interesting question. So one thing that I want to point out, unless you are a practitioner in the field, is that there is a little bit of difference in the advanced transistors between gate length and channel length. So replacement gate transistors that are the advanced gate transistors today, this is the gate length, but then you have spacers, and that's the channel length. Okay, so based on many calculations that were done in the early 2000s, we know that if we can go down to around 1 nanometer silicon and say 6 angstrom EOT gate oxide, this is something that that has been simulated by actually groups at Purdue. They show that the channel length can be of the order of 6 to 7 nanometers, so here to here, which for a gate length will mean 2 to 3 nanometer, right? So that's, yeah.
Okay.
Thank you. Excellent talk. I had actually two questions. The first one is, do you find that you have to deal with a lot more noise when you make the silicon very, very thin? And then my second question is, how easy is it to manufacture these mixed capacitors that have both dielectrics and ferroelectrics in them?
I think the first question is a very good one, and I'd say that I will interpret it slightly differently, in the sense that perhaps you are asking that are there a lot of thickness variation in that very small thickness, because the same amount of variation will look much lower when that overall thickness is high. That is definitely a question we don't know the answer to. In terms of real device noise, we don't see anything. However, to look at the thickness variation, what one has to do is to measure many devices that industry can do, and then see if the variation is going up or not. So that's one thing. The other thing is that talking to some of the industry people who are very good at synthesizing materials, industries that grow materials, they seem to be confident that if needed, they can grow extremely thin materials with very good uniformity, except that they're not doing that today because that's not what we needed. So I'm hoping that it will be possible to grow very uniform materials with small thickness, but that needs to be seen. The second one is, as I showed, that this mixed ferroelectric dielectric stuff that we have worked on for many years is already in our products. So if you bought any computer products after 2020 that uses a Samsung DRAM, you are essentially using it. So
I'll kind of follow up on this material uniformity question. So you've shown this, ferroelectric polarization, which has the W-shaped potential, but I assume these materials are non-uniform, they're not single crystal. So I'm imagining, part of the gate might be operating in this regime that you plotted, but there might be other parts which are still switching between different macroscopic polarizations. So can you comment on the role of disorder in the material and how it impacts the device?
So, very good question, and there are two parts of that question. So, of my answer, the first part is we actually want mixed phase. We want ferroelectric, dielectric, all of that, because of this. What we have seen is that this frustration of polarization gets amplified if you have the mixed phase, because ferroelectric polarization does not want to go directly from here to here. There's a lot of energy. So inside, if you have some dielectric, it can reorient itself, and then you get a lot of negative capacitance. Now, the second part that you are saying, of that having a mixed phase, I think, in trouble if my device is really small from all dimensions. But when we work with these things, you think about it, the overall width of the device is actually pretty large. It's still around 100 nanometer or so. So even on a fin, the channel length maybe 16 nanometer or 18 nanometer. But if you look at the overall wraparound area of the fin, that is still around 100 nanometers. So it gets averaged out. We have actually seen from a work from Global Foundries, industry level variation data on this kind of structures, and the variation actually looks better, but there is a reason for that, which is not with to do with the materials. But what that shows is that the variation probably is under control.
One more follow-up question.
Let's give one to Elon, and then you can get
Yeah. So you projected the operating voltage of 0.3 of a volt, which would be very nice. Where is industry now?
700 today. I have asked many of my industry colleagues, where do you think that we can go to? I get different answers, but I have, so far the lowest I have heard is 600 for various reasons. My moonshot, you see that what I said, moonshot is 250, because there is something that people have not really talked about a lot, but I think it needs to be talked about when we start going there, is 250 is just 10 kT. And once you are there, I think the overall SNR for that switch also needs to be looked at, because during the E3S days, we started talking about it a little bit, because if you set a off voltage, and so you need a little bit of range for off and little bit of range for on. If the overall is 250, just 10 kT, whether or not just some noise can just switch you from off to on, there are some questions about that we need to see. I believe that 300 millivolt we will reach. 250 is my moonshot.
So do I have 700 in my cell phone?
Depends on which node you are using, but I would say that you do, but they're not using 700 most of the time. Most of the time, you are running at a much lower voltage, much smaller clock speed than what it is spec'd for, because they just don't want to drain your battery.
Okay, I think what we'll do is we'll bring the formal part of the presentation to a close. I think Professor Salahuddin will be willing to stick around for a few more questions that are lingering. But I want to thank Professor Salahuddin for a very exciting and illuminating talk, which confirms what I promised, which is that contrary to the wishes of many computer scientists, paradoxically, Moore's law is not dead. We're going to continue to make transistors smaller. We're going to continue to lower the voltage. We're going to continue to improve the performance of our electronics from the bottom hardware layer. And this is, I think, good news for everybody. So thanks very much to Professor Salahuddin. Thank you all in the audience. And
Thank you. Thank you. Thank you.